to get further practice with working with transient material balances, in this video we're going to focus on a relatively simple unit operation. We're going to focus on the batch reactor. Now, you may have heard this term when you worked with reactive material balances in both MEB1 and also in this course. And so with the batch reactor, it's a closed reactor system. Okay? And typically one would use a batch reactor when they're doing some sort of small scale operation, or they're trying to test out a new process or something that's difficult to make continuous. Alright? And so typically used for small scale operation, testing out a new process, so that you don't really want to use that much material because you don't know if it's going to work. And also some processes where you really just can't make it continuous, or difficult or impossible to make continuous. And really some examples of types of batch reactors include many of the bioreactors they use for growing cells. And that also includes, for instance, brewing beer, where you have to let your sort of beer mixture ferment for a long time. Okay? Now, to give you concrete examples of what batch reactors look like, I'm just going to go here to my extra slides. And so batch reactors, they're typically used for small scale operations, but even still, they greatly range in size. For instance, what you see here is an image of a batch reactor that fits right on a laboratory stir plate. Okay? And so they're doing a very small scale reaction with this batch reactor. Well, on the opposite end of the spectrum, you could also make fairly large batch reactors. And so the one you see here, you could see that there's a person, operating it at the moment, setting it up. And you can see that this batch reactor is taller than the person. Okay? And so batch reactors range in size. Now, some advantages, or the main advantage of using a batch reactor over other types of reactors, is that with a batch reactor, once you start the reaction, you could leave your reactants in there for a long time. Reactor for a long time. And so that's part of the reason why batch reactors are typically used in bioprocessing, because a lot of the reactions in bioprocessing require a long incubation time or a long residence time. As we saw in problem 4 on homework 10, for example, the bioreaction that was going on there, that took 220 hours. And so batch reactors are good for cases where you need your reaction to run for a long time. Of course, the disadvantages for using a batch reactor is, even though you could just leave your reactants to run in the reactor for a long time, you still need to watch your reaction to make sure that it's properly running. And also, loading and unloading and cleaning the reactor also require a lot of labor. Okay? And so for batch reactors, there's a high labor cost per batch. The yield and the purity of the products in a batch reactor can vary greatly. And also, as far as scale up is concerned, it's hard to scale up your process just based on using a batch reactor. And that's not only due to challenges in scaling up the material balance, but also challenges when you scale up the energy balance as well. Okay? Alright, but on that topic, The reason I bring up batch reactors now is because working within material balances are relatively simple. And so that's what we're going to focus on now. Let's go into the batch reactor material balance. To derive this material balance, I'm first just going to draw a sort of simplified diagram of what a batch reactor looks like. So we have our reactor, and we also have a stirrer in there. And let's say we have a batch reactor full of some, liquid reactant, okay? And what I'm going to say is that the volume of the liquid, of the reacting liquid in this reactor, I'm just going to say that's the volume of the reactor. And not really the volume of the vessel, okay? All right, and so that's going to be the diagram for our batch reactor. Let's now go to the material balance. So we'll start with our general material balance equation. Accumulations equal to input minus output plus generation minus consumption. So with the batch reactor, it's a closed system. There's no mass that crosses the system boundaries at any time. So our input and output terms, those are going to be 0. And I'm just going to write closed here. Okay? All right. And so what that means is for the batch reactor, really the only terms we need to care about in our material balance are the accumulation term and also the generation and consumption terms. All right? Okay? And so let's say in our batch reactor we cared about, the reactions involving some species A. So for the accumulation term, when we're dealing with this reaction, what we want to track is the moles of A over time. For the generation term, the way I'm going to write it as the product of two variables, where we have something called R sub gen, and then also the volume of the reactor. Okay? And so the volume of the reactor here, which I'll write again, that's going to have dimensions of length cubed. And this R term, this is what we call the reaction rate. Okay? And this has dimensions of moles per time per length cubed, such that when we multiply the reaction rate by the volume of the reactor, we end up getting just moles over time, which matches the dimensions of the accumulation term. For the consumption term, we're going to write something similar, where we have an R consumption times the volume of the reactor. And so if we plug in these terms back into our material balance relationship, what we get is our dNA dt is equal to the reaction rate of generation times the volume of the reactor minus the reaction rate of the consumption of A times the volume of the reaction. Okay? And so I'll say that this is the general material balance equation for batch reactors.